Okay, illustrative math, Algebra 2, Unit 4, Lesson 13 is called Exponential Functions with Base E. So, quick review here. Make sure you remember what E is. E is approximately 2.718, and it keeps on going. It doesn't repeat. It does not terminate. We learned what it comes from in the previous lesson, which I believe was 412. So if you're not sure where that comes from, go back and watch that video. All right, so our goal today is I understand that E is used in exponential models when we assume the growth rate is applied at every moment. So we've learned that an exponential function is y equals a times b to the x. A is your initial value, b is your growth factor, x is usually time, y is your final amount, okay? So b, remember b is really 1 plus your growth rate. Okay. Now, this model is good. It's simple. It's easy. That's why we learn it first. But the problem with this is it's not continuously applying the growth at every single moment, every second, every minute of every day. It's just applying it like once at the end of each year or at the end of each time interval. So what we do is we kind of like modify this if we want it continuous. We say y equals still a times e to the r. So instead of adding 1 to your r, you just put r up here as a decimal times t or x. Okay, I'll just use x because that's what I used here. But these are basically going to give you the same graph. This one will always be a little greater because your growth rate is continuously applied at every moment, whereas this is only applied at the end of each interval. Okay. So like if X was every year, you'd only be growing once per year at the end, whereas this is like throughout the year, every moment of the year. Okay. So warm up. The other day you learned that E is a mathematical constant whose value is 2.718, which we just talked about. When working on problems that involve E, we often rely on calculators to estimate values. So find the E button on your calculator, experiment with it to understand how it works. For example, see how the value of 2E or E squared can be calculated. Usually most calculators come with E to a power, so it'll have an E with a power, with a little caret there. So if I just want E, I might have to put to the first, depending on which calculator you have. The 84, I believe it gives you like a dotted box right there, and you can just put the 1 in there if you just want E. So if I wanted to do 2E, I'd have to do 2. If I have this calculator, the TI-30X, I'd have to do 2 times E to the first. If I wanted to do E squared, I would just do E to the second like that. That's on this TI-30X2S. If I had the 84, that one you could type it in as E to E, just like that. I think you'd have to put to the first. Okay, or if I wanted to do E squared, I could just do E, and I just put a 2 in there. Okay, so I did screenshots of the calculator so I can show you where they're at. Your E button on the TI-30X2S is right here. So you got to hit second first, hit this button, and then hit the LN button, and it'll pop up like that. It'll say E to the what? I think it'll give you a caret with a parenthesis. Let me double check. I have one right here. Yep, it'll look exactly like that. All right, now this one here, your E button is right here. So you got to hit second and then hit that button, and boom, that'll pop up. It'll look like this. It'll be like E, and it'll have a little box right there. Okay. All right. So go ahead, type these into your calculator. Make sure you get the right value. If you want to pause the video, you can, but make sure you get, when you type those in, you get what you're supposed to. Another thing here with fractions here, I would put it in parentheses probably, because if you don't, your calculator will do e to the 9th and then divide it by 23. If I type it in like that, e to the 9th, And then if I hit divided by 23, it might just take it to the ninth and then divide the whole thing. That's not what we want. So you can avoid that by using parentheses. Same thing here with this, like, again, make sure that when you type this in, you don't type in for B, you don't put 5 times E to the 1.1 times 7. I would maybe multiply those first and just make it to the 7.7. Okay, so play around with your calculator. Make sure that you know how to type these in, because it would suck to do the whole problem and then like you get it wrong because you typed it in wrong. So make sure you can do all these and get these right answers. But everybody has different calculators, so there's all kinds of different ways it might pop up on there. All right, so let's compare these two functions here. Population of a colony of insects is 9,000 when it first being studied. Here's two functions that could be used to model the growth of a colony. I should say T months after the study began. Okay, so this is like applied every month. This is the old function. Okay, growth is applied every month. And this is continuous growth. Continuous growth. Continue. Can I spell? Okay. So basically here, 9 is your initial value. 2% is the percent you're growing at. So here you have to add it to 1 to get your base. This is that y equals a times b to the x. And this is y equals a times e to the rx. Okay, so your rate is 2% on both of those. This one I use a base of e. So I'm going to plug all these numbers in for t, and make sure you get the same numbers. Make sure you're using it on your calculator properly. But I already typed them in here to speed things up a little bit, and you should get these values. So there's the first part. And then I come here. What do you notice about the populations of the two models? So they're very close. 10.14, 10.15, 11.41, 11.44. They start to separate the bigger you get. Okay. So what do you notice? I would just say populations are very close, but the population that is growing continuously is a little larger and continues to separate more as t gets larger and larger. Okay. Oh shoot, I spelled continuous wrong. Continuous growth. Okay. All right, so third part. Here are pairs of equations representing the populations in thousands of 4 insect colonies in a research lab. The initial population is 10,000, so that's why we get the 10 in the front of all those, and they're growing exponentially. T is time in months since the study began. Graph each pair of functions on the same coordinate plane. Adjust the graphing window to the following boundaries. So I have those all graphed. I'm going to show you on the next couple slides. What do you notice about the graph of the equation when using E and the counterpart written without E? Make a couple observations. All right, so here's our first function here. So you start, 10 is your initial value, 5% growth rate. Okay, 5% growth rate. So this one's continuous on the bottom. And this is applied every month. So what you notice is the one on the green graph, or the not the green, the blue graph is always a little bit bigger than the red. Okay. They start out really close, and then as your months go on, because this is months on the X, and this is your bacteria, I think, on Y, the blue starts to separate. It starts to be greater. Now, some of you might say, well, the red is to the right. We're not looking to the right. We're looking which one is above. So, like, let's look at 40. At 40, the blue is here, the red is there. The blue is greater at 40. Okay. Same thing happens here. This is 3% growth. This is using that new function. So this one is continuous. And this is applied monthly. So obviously you have to like kind of look real close there. The blue starts to get a little bit greater than the red as time goes on. They start out almost identical and then they split. Okay. And then same thing here. The problem is you can't even see the red. They're so close that they're almost on top of each other. You can't, the pixels aren't even close enough. So the red one is underneath this blue. This is a 1% growth. And what's happening is as your percentage is smaller and smaller, the difference between them is less and less noticeable. Okay, this is 0.5% growth. And you can tell both of these are almost not noticeable. So I'm going to go back. I'm going to answer that question here. I'm going to say, I would say the graph using E, which is growth rate continuously applied, is always a little greater than the graph that does not use E. Okay. And I would also say as the growth rate gets larger and larger, the difference is magnified. The difference between the two with a very small growth rate is almost not noticeable. Okay. Okay. So that would be my answer. Okay, so here is kind of what we talked about. Your book kind of shows you some things here. This is obviously your, let's see here. Let's see if I can write this in here. This is your final value or your total. This is your initial value. E is obviously 2.718 approximately. R is your growth rate as a decimal. All right, don't put in, if your growth rate is 6, don't put in 6, put in 0.06. So here's some examples here. At time t equals 0, measured in hours, scientist puts 50 bacteria into a gel dish. Bacteria are growing and the population is expected to show exponential growth. So here's my function. So 50 is your initial value. 0.25 is your growth rate. So that's as a decimal. So I'd have to move it 2 to the right. So it would be 25%. All right, 1964, the population of the United States is growing at a rate of 1.4% annually. That year, the population was 192. So that's my initial value, 192. And if I'm growing at 1.4% annually, I have to convert that to a decimal. So it's 0.014 times t. All right, so there we go. There's our continuous growth rate, which we already had there. All right, 1955, the world population was 2.5 billion and growing. The model predicts population in billions of years, so the 2.5 will go here if it's in billions. And then what's your growth rate? So this is your growth rate, so 0.0168. I have to move my decimal 2 to the right. So I'm going to get 1.68%. Okay. All right. Use graphing technology to graph this function. Oh, shoot, I have a double slide. All right. So use this graphing technology to graph this function here, 50, which is the first one we had. Just the window as needed to answer these questions. Okay, so here's my function. The function f models the population of bacteria in t hours after it was initially measured. So this is going to be the number of bacteria, and this is going to be hours. Okay. About how many bacteria were in the dish 10 hours after the scientists put the initial 50 in? So for 10 hours, of course, my graph doesn't go far enough. So, of course, I didn't make my graph big enough. But what I would have to do is I'd have to go out here till I got to 10. Okay. And whenever I get to 10, okay, I'm going to go up and I'm going to find out where it hits my graph. Okay. So, if my graph were to continue going up like that, I'd go up here to 10 and I'd find it on the graph. Okay. So since I have a function, I'm going to do this. I'm going to just plug in 10. I'm going to say f of 10 equals 50 times e to the 0.25 times 10. All right, and I always like to multiply this first because sometimes people, if you try to type it all in, your calculator will only take e to the 0.25, and then it'll multiply the whole thing by 10. So I would do 0.25 times 10, and I'm probably going to get 2.5. So I'm going to probably type it in like this. 50 times e to the 2.5. And that gives me 609. All right, and I think it was in, let me go back. What was that in? That was in, it's just 50 bacteria. Okay, so it's not in thousands or anything like that. 609 bacteria. All right, well, how many hours did it take for the number of bacteria in the dish to double? So if I double, I need to know when I get to 100. Now that I did leave enough room in my graph. So if I start with 50, when do I get to 100? And it looks like it's 2.8 maybe. So I would say approximately 2.8 hours, okay? Now, if I were to do that with the equation, you'd plug in 2.8 for t, you get 50. I'm sorry, wait, we wouldn't know 2.8, so we'd have to say 100 equals 50 times e to the 0.25 t. Now, the problem is this is an exponential equation, so we haven't really learned how to solve that other than trial and error. So you could plug in a bunch of numbers for t and see when you get 100. That would work, but we're going to learn some algebra techniques a little bit later as we go. All right, here's another one. 192, that's my initial value. So this means my growth rate is 1.4%. So the equation models the population in millions in the US T years after 1964. So this is years after 1964, and this is our total population. All right, in millions. Put an M there for millions. Okay, so the equation models the population in millions in the US years after 1964. What does the model predict for the US population in 1974? So that means that T is going to equal 10, because 10 years after then. So it says, what does the model predict? So I'm gonna plug it in instead of looking at the graph. 192 times e to the 0.014 times 10. So I'm going to multiply these first, and I'm going to get 0.14, so that way I don't mess it up. So 192 times e to the 0.14 gives me 220.8 million people. And again, if I look at my graph here, if I wanted to go to 10, a little bit less accurate, but it still works. I can kind of, get pretty close there. I can see, oh, looks like these are going by 20s because there's 1, 2, 3, 4, 5 of them. So yeah, it looks pretty close to 20. All right. Obviously, this is a little bit more accurate using the function. All right. In which year does the model predict the population will reach 300 million? So 300 equals 192 times e to the 0.014 t. So again, since your variable is up here in the power, you're going to have to just guess and check for now. Or you could use the graph and say, okay, well, 300 million is right about there, which goes to 32 years. Okay. So there's that. Okay. All right. So here's two functions. They both kind of represent the same thing. This is just continuously growing. And it's at it's at 0.5%. So it's 0.5%. And this is growing whatever t is. If it's every year, it's growing 0.5% at the end of every year. If it's every month, then it's 0.5% at the end of every month. Okay, so this is growing 5% every t units. Okay, I guess units of time. So first form can be used to represent both discrete and exponential functions. The second form, using base e, is used only to represent situations where change happens continuously. Okay, so that's basically kind of what I wrote here. This is only happening at the end of every time period. So that's why we say discrete, because technically it's not happening continuously, but we generally accept it to be continuous and we connect the dots. This is happening always, every second of every moment. All right, so I understand that E is used in exponential models when we assume the growth rate is applied at every moment. All right, so here is a function, and here's another function. Each model the population of a city in thousands 2 years after 2010. Describe how each model predicts the population in the town will grow. Okay, so our initial population is 8.75 thousand for both. Our growth rate is 1%, because this is 1 plus my rate, and then this is just my rate right there. B of t is growing continuously. And A of t is only growing once, and it's at the end of every year. And B of t will always be a little bit greater than A of t because it's continuously growing. Okay. All right, so that's it for today. Thanks for watching. Hope you enjoyed this video, and we'll see you next time.